Thank you very much, Alexei, for the introduction. And first of all, I would like to thank the organizer of this very nice workshop and all the NeoSpec team, especially Philipp Schaffer and Robert Staber for their support in exploring and expanding the application of the NeoSnom. I will challenge your attention with a little bit change of topic, because as my title suggests, I'm going to talk about photocurrent near-field microscopy in the terahertz range. This technique relies on the measurement of photocurrent and photovoltages when a sample is illuminated in the near field, in our case by terahertz radiation. To perform this type of measurements, you need a high-power source, which in our case consists in high power, milliwatt power, terahertz quantum cascade lasers. And with this technique, we can achieve a spatial resolution in measuring the photocurrents and photovoltage of about tens of nanometers, which in the terahertz range is incredible. It corresponds to a fraction of 1/1000 of the incident electromagnetic radiation wavelength. To perform these measurements, of course, you need to have electrical readouts. And by exploiting the zapping operation of the NeoSnom, we can isolate the near-field contribution to the conduction by demodulating the electrical signal at the harmonics of the tapping frequency. I would like to dive into one of the application study that we have performed in Pisa. About one-dimensional materials. In this case, is consisting of indium arsenide nanowires. These nanowires are very promising for detection of terahertz radiation because they have high mobility and up to farad capacitance, which make them interesting as building blocks for fast electronics. They were prepared in Pisa at the NEST laboratories by chemical beam epitaxy. You can see an example of forests of nanowires. And back already in 2012, they were coupled into field effect transistor and a bow tie antenna to couple with the terahertz radiation in the far field, and demonstrated interesting noise equivalent power that even allowed to perform far field imaging with the nanoscale detectors. Interestingly, the responsivity of these detectors depends strongly on the carrier density. But what was the mechanism at the base of their ability to work as an efficient terahertz radiation detector, even at room temperature, was still yet debated and unknown. So here comes our study. Basically, the photodetection mechanism that can come into play at terahertz radiation, at terahertz frequencies, are three. The thermally driven photothermoelectric effect, the volumetric effect, and the Diakonow-Schur mechanism, which is the rectification of terahertz radiation by plasma wave, with that in the non-resonant regime gives rise to a very broad response and relies on an asymmetry between the source and the drain contacts. But let's have a look at the thermally driven effects. The photothermoelectric effects can arise in a material which has a non-negligible Seebeck coefficient, and that is spatially varying across the material. And this type of material can convert the absorbed light into a photovoltage, which arises every time that we have a gradient in the electronic temperature. Instead, the volumetric effect relies on the heating of the lattice, and it's present every time we have a conductivity which depends on temperature. But in order to measure this effect, we have to apply a bias and monitor the variation of the conductivity. I would like to convince you that near-field photocurrent is a powerful tool for distinguishing this different mechanism. We simulated the effect of the illumination with the AFM tip of the nanowire. You can see a 3D finite element simulation by Compson Multiphysics. Sorry, there was a movie, okay. We actually evaluated what is the field distribution on, across the nanowire as we scan the tip. And what we observe is that the energy loss in the nanowire is peaks at the position of the tip on the nanowire. From that, we can resolve the one-dimensional heat diffusion equation to see what is the profile in the electronic temperature and lattice temperature that result from the near-field excitation. This is the result as a function of the actual coordinate of the nanowire and the position of the tip. We can take some cuts to see what's the profile in the electronic temperature and lattice temperature at a precise position of the tip. As you can see, this local excitation is creating a gradient in electronic temperature, and it's also creating a variation in the lattice temperature. So, in principle, it's able to give rise to these, the thermally driven effects and photocurrents. And interestingly, the two effects would give rise to very distinct line profiles, because in the case of photothermoelectric effect, we would expect to see a change in the polarity, because the electron will go towards the cooler part of the material. So, as the tip moves across the nanowire, we will see a change in the direction of the electron flow. Instead, in the case of bolometric effects, we will see the highest current, where we have the highest lattice temperature, and a constant polarity across the nanowire. We mention another possible effect, which is the plasma wave excitation, which arises and can be in principle be detected by near-field photocurrent nanoscopy, because the AFM tip is there is a capacitive coupling between the AFM tip and the electrodes. So as the tip moves across the nanowire, we can see a photovoltage which arises from this coupling. And we expect to see a line profile similar to the photothermoelectric effect, so with a change in polarity as the tip scans the sample. We can distinguish this effect from the photothermoelectric effect because in this case we expect to see a variation with the bias, because the current will increase the asymmetry between the electrodes and enhance this response. So let's go to the data. We have tried tons of nanowires with different length and different distance between the lateral gates that we use to tune the charge carrier density and the nanowire. So the capability of tuning the carrier density within the nanowire. And without applying any bias, the first response is a current with a constant polarity along the nanowire. So, as we said, a bolometric fingerprint. But as we increase the gate voltage, we always found a threshold at which the photocurrent profile completely changed, with the appearance of a clear phase change, polarity change at the position along the nanowire. So we see that there is, at the high carrier density regime, the photothermoelectric effect or the plasma wave effect are dominating. In order to distinguish in between the two, we analyzed the variation with the bias, and we saw that in the high carrier regime, where we have the change of polarity, the photovoltage is constant. So we can say that in this regime, the response is dominated by the photothermoelectric effect. The fact that this effect becomes dominating over the bolometric response at the high carrier density is not so surprising because of the correlation between the Seebeck coefficient and the carrier density. We can try to evaluate the Seebeck coefficient starting from the transconductance curve, so the current change with the voltage, and estimate the Seebeck coefficient. I'd like to say that the two mechanisms are present in a nanowire, in this type of material, and we can enhance the volumetric effect by increasing the current so that it becomes dominating even at high voltages, at gate voltages, when we would expect to see the photothermoelectric effect. So the photothermoelectric effect has some advantages over the volumetric mechanism for detection, because it needs no bias. So we can get rid of a lot of sources of noise. And also because it's exploiting the positive correlation between the LED temperature and the stable coefficient, we can, it can support room temperature detection. And because it relies on the electronic bath heating, it would support the detection at higher speed. In order to exploit the message that we have obtained from our near-field study, we optimized the device architecture by coupling the nanowire with a monosymmetric antenna, which is favoring the gradient in the electronic temperature and enhance the photothermoelectric response. Another possible strategies that we are exploring is to have a non-uniform doping profile along the nanowire, or using twisted structure. And I would like also to say that volumetric effects can be an advantage if you have to work at low temperature, and it can be enhanced by using suspended architecture that quench the processes that release the lattice heat to the environment. With that, I would like to conclude, hoping that I have convinced you that this technique is a powerful tool to distinguish the different photodetection mechanisms. By seeing Pablo in the first row, I would like also to say that it's a powerful technique also to explore collective excitation in the material, because the interference-free pattern that is created by the polariton propagation can give rise to a modulation of the energy dissipation along the material that modulate the currents. And with that, I would like to thank all the group in Pisa, especially the people involved in this study, and you, of course, for your attention.